We're going to start with section 3.1, which is measures of center. And the focus of this section is to obtain a value that measures the middle or the center of our sample data, the center of the data set. Okay. So our goal is to obtain a value that measures the center that measures the center of a data set. That's our goal today. And we're going to discuss three ways to measure the center. The first one is the mean. The second one is the median. Third is the mode. And the fourth one is the mid-range. All right, so these are the four different measures of center that can be used to describe the middle of this data set. Let's begin with the mean. Number one, the mean. So the mean has two different symbols. If the mean is associated with a population, meaning if we have population set and we are finding the population mean, then we're going to use this symbol mu, Greek symbol mu, and basically it is the sum of all the x values, all the data values, divided by capital N, where capital N is the population size. So sum, the sigma here means sum of all data values, and then N is the population size. Okay. Example. Consider the following. Population set. So we're talking about all the numbers we have in this set. 12, 5, 36, 7, 18, 9, 4, 10. Let's see how many data values we have. N, capital N, the population size. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 values. And we want to find the population mean. So we're going to add all the data values we have. 12 plus 5 plus 36, 7, 18, 9, 4, and 10. The sum of all these values, and then I divide by the number of values I have, which is the population size divided by 8. That gives me 101 over 8, which is 12.625. Now, there is a statistical rule here. When you're trying to find the mean, you always go one decimal value above your data values. So now, since my data values are all whole numbers, since I have all whole numbers here, then I need to round my population mean to one decimal place. So that means I'm going to say at the end, my population mean is 12.6. I rounded my value to one decimal place. So that's a statistical rule. You always go one decimal place above or over the data values that you have. So 12.6. So notice here I used mu for the population, for the mean in this case, because this is a population set. Okay, my next thing is sample mean. The symbol that we use for the sample mean is X bar. X and then bar on top, and this is the symbol for the sample mean, and it's equal again to the sum of the X values divided by small n. Small n means the sample size. So sum of X here, means the sum of all sample data values, and n is the sample size. Example. Suppose I have this sample data, sample set, which is, let's say I'm going to take 4 numbers from the set that I have above, let's say 12, 36, 9, and 10. Only these 4 numbers. I want to find the sample mean. X bar is the sum of all the X values over n. So that means 12 plus 36 plus 9 plus 10 over 4. I have only 4 values, and that gives me 16. Let me check here, 67. 67 over 4. And that is, again, I round to one decimal place, so 16.8. X bar for this specific sample. For this sample, the sample mean is 16.8. Okay. Any questions on the symbols or the notation that I'm using for finding the sample mean?
No.
Okay, good. Let's move on to our next measure, number 2, which is the median. Let me give you the definition. The median is the median of a data set, is the measure of center that is in the middle, that is the middle value when the original data values are arranged in order in an increasing order. Okay. Example on calculating the median. The median. Consider the sample data (14.1, 22.4, 23.1, 38.5, 46.3, and 55.6. Find the median Okay, so finding the median, I check and look, is my data set already ordered in increasing order? Do I have an increasing order here? Yes, 14, 22, 23, 38, 46, 55. Yes, so I do not change the order of the data values. It's already been ordered. So what do? I count, I see how many values do I have. So let's put them here, 14.1, 22.4, 23.1, 38.5, 46.3, and 55.6. I can say that here my sample data, my sample size is 6. And because I have even number of data values, then that means I have 2 numbers in the middle. 2 numbers in the middle. These numbers are what? These 2 here. 23.1 and 38.5. These are the numbers exactly in the center. Now, what I'm going to do to find the median, I'm going to take the average of these two. So 23.1 plus 38.5 divided by 2. 23.1 plus 38.5 divided by 2. 30.8. And that's the median. Now, in this example, I'm gonna give you an odd sample size, an odd number of values. Again, consider this sample data. Uh, 12, 19, 10, 20, 12 again, 18, and 24. So these are my values. I have what, 3, 6, 7 values. So I want to find again the median. So in this case, I need to order the numbers, increasing order first. So I have what? I have 12, and then another 12. Oops, I have 10 first. So 10, and then 12, 12, and then 18, 19, 20, and 24. I have 7 values, so that means there is only one number in the middle, one number that separates the list into 2 parts, equal parts, which is what? The 18. You have 3 values on the left and 3 values on the right of this number, exactly in the middle. So the median is 18. Okay. All right. The third measure is called the mode. The mode of a data set is the value, or it could be 2 values. There could be more than one. It's the value or values that occur with the highest frequency, or with the greatest frequency. Example, find the mode of the sample data. Point 2, point 3, point 3, point 2, 0.3, 0.6, and 0.6. You can see that we see repetitions here in our data values, but which one of these data values is repeated the most? You can see that it is the 0.3. There's one here, another one here. This is the one that has the greatest repetition, greatest frequency. So the mode is 0.3. Okay. Now there is a possibility. I just want to write a note for you guys here. Note. There is a possibility that the data set could be bimodal. There could be more than one value with the same repetition, same frequency, or there's another case where the data set has no mode. No mode because all the values are repeated the same number of repetitions. So it is possibility, there's a possible for sometimes to have a bimodal set and also in other cases no mode. Okay. The last measure of center that we're going to discuss, I think we talked about the mode, the median, the mid-range. Number 4, the mid-range. And the mid-range is another way to measure the center, to describe the center of the sample data. And it is equal to minimum value plus maximum value. So you take the smallest value, take the largest value, you add them, and you divide by 2. Lowest plus largest, sum divided by 2. So example, here's a sample data. 2.4, 1.6, 8.4, 3.5, and 7.1. Mid-range is, let's see, what is the lowest value we have here? Lowest value is 1.6 and the largest value is 8.4. 1.6 plus 8.4 divided by 2. And that will give me 10 over 2, 5. I'm going to ask the questions. Are you ready? Excellent. Thank you. Okay. Kira, you have a question? Okay, excellent. All right. So these are the 4 measures of center. Guys, now I'm going to show you how to use a calculator when you have a large sample data. TI-84 plus can be used to find these measures, to find the median, the median, the mean, the median, and the mid-range. I want to show you how to use your calculator. So let me give you this sample data. So I have 2, 4, 6, 8, 10, 12, 14 values, and it's 14. This is again a sample. Okay. Guys, this is what we're gonna do. I'm gonna switch screen. I'm gonna go to my desktop screen. So just 1 second. All right, so you can see, guys, on the left of your screen, it says here TI-84 plus. So this is exactly what you have on your calculator. This arrangement here of functions is on the calculator TI-84. So let's say I want to find the mean and the median for my sample data. what I'm gonna do first, I'm gonna click on stat. Okay, and then I'm gonna select or press 4 for clearing. Yeah, I want to clear the list first. I want to make sure there are no numbers stored in the calculator. So clear, and then I'm gonna press second L1 to clear L1. We have L1 through, I think, L6. We want to just use one list, so we're going to clear L1. And then you're going to press the C again. And then we're going to edit, press 1. Then we enter our value you see here on calculator screen. So L1, and I'm going to enter my data values. $18, $10, $5, $21, $17, $5, $17, $9, $15, $12, $20, $20. So you can see, guys, here I have entered 14 values. The calculator says enter 15. I do not have 15 values. I only have 14. So I have 14 values entered. Okay. And then I'm going to go back after entering my values into L1. I'm going to press the stat key, and then I'm going to move to calculate, moving my cursor now to the right, calculate, and then I'm going to press 1 because we only have one variable and we want to get this variable stats. So we're going to select 1. And it says here now the list is in L1. Frequency list, don't worry about it. There is no frequency here. These are just the original set. We have the original set, so keep this blank. And then go ahead and select calculate and then enter. And the first value that is the sample mean. The sample mean, X bar, but you need to round it to 14.9. And then it gives you the sum of the values, the data values, the sum of the squares. And it's going to give you also, we're going to discuss these in a minute, in the next section, the standard deviation, the sample standard deviation. And it gives you the minimum value and the median. See here, this is the median, and gives you what we call the quartiles. I'm going to discuss the quartiles also in the next section, and then the maximum. All right, all these values are available using the calculator. So first, I'm going to write down the mean, 14.85, and the median is down here is 16. I'm going to round. So X bar is 14. I'm gonna round to 1 decimal digit because all my data values are whole numbers. 14.9, and the median is 16. Now, as far as the mode, you need to go back and just look at the set and see if you find any number that is repeated the most, then that's your mode. I see the 5. One 5 here, another 5 here. What else? I see another value that's repeated, the 20, 20. The 17. The 15. Right, they all have the same frequency. So I'm gonna say, in this case, the 5, the 17, or the 15, the 17, and the 20. We have multimodal set in this case. Okay. So the calculator gives me the mean. I rounded it to the 1 decimal digit, the median, and then I looked at the data set and I found these numbers that have the same frequency, repeated the same number of times. So this is my mode. Okay, questions? All right. Let's go ahead and move on to the next section. Measures of variation. So in the previous section, we talked about different ways for describing the center of the data set. But now we're going to focus on another characteristic, another attribute of our sample. We're not going to discuss we already discussed the center. We're going to talk about the variation in the sample. We want to see how much variation we have among our sample data. Are all the numbers very close to each other, very close? Or there is, they are spread apart. There's large differences between the numbers. Okay. So I want to explain, guys, this sketch here. I have 2 bell curves want to show you two normal distributions or bell curves. Sorry about this. And this one. Okay. So these two samples, this is sample 1. And this is sample 2. What is in common between these two samples? If I have two sample data, one sample taken from a population, another sample two taken from another second population, what do they have? They're both have the same type of distribution, meaning that the majority of the data values are in the center. A lot of data values in the center in both of them, and then very few data values on the sides. So we have a bell curve that is, spread, have a range. This is the this is the range of the first sample. Bell curve, very few values at the beginning, and then the frequency of the values starts to increase, reaches a maximum, and then goes down to a low frequency. The second one is the same. Again, the majority of the data values are in the center, in the middle, and then a few values in each tail. Again, bell curve, normal distribution. But the range in the second sample, is much smaller than the range of the first sample. So the spread, the data values in the first sample have more spread, more range. They are spread out more than this data values in the second sample. Second sample, the data values are centered in the middle, and few values a little bit above and few values below the mean. But for the first sample, the spread is much, much more than the second one. So we need to measure, guys, the variation in our sample. And there are 3 measures, okay? 3 measures of variation. The first one is called the range. Okay, and the range can be easily calculated. It is the maximum value minus the minimum, the difference between the largest value and the smallest value. Okay. And the second one is called the standard deviation. And the standard deviation, the symbol for the standard deviation is S, and this is the sample standard deviation, S. And there is another symbol for standard deviation, which is sigma, and it's for the population standard deviation. population standard deviation. Okay. Here's the formula for the sample standard deviation, S. It is equal to the square root of the sum of x minus x bar squared over n minus 1. This is for the sample. Let's box this here. This is the sample standard deviation. If you have sample data, then this formula gives you the measure of the spread of your data, whether it's a narrow sample that has data values very close to each other, or whether the sample has data values that are widespread from each other. Now, if it's a population set, okay, population set, then we're going to use sigma, and sigma is again the square root of the sum of x minus mu square. So we're going to use the population mean, and then divided by population size. Okay. Now, in general, we're going to be using this formula, the one on the left, because most of the time we're going to be working with samples, not populations. Okay. And let me try to explain what this formula says. Guys, if you look at this here inside the square root, you see this? Oops. This part here. This means that the difference between a data value and the sample mean. Okay. You are finding the difference, all of these differences between each data value and the center. Okay, and the center. And you're taking those differences and you're squaring the differences, and then you're finding the sum of the squares, the sum of the squares. Dividing by n minus 1, right, to take the average of these differences, and then the differences of the squares, and then taking the square root, and that will give you the average of the average variation or standard variation. Okay, so this is what it means. Same thing for the population mean. You're taking the difference between each data value and the population mean to get the population standard deviation. Okay. And the third one, oops, is called the variance. And the variance is always the square of the standard deviation. This is for sample variance. And you have also the population variance. Which is sigma squared. So after finding the standard deviation, if you square that number, you get another measure that is called the variance, the sample variance and the sample and the population variance. Okay. Example. Any questions, guys, on this? All right. So example. Calculate the sample standard deviation and sample variance. And since we're going to do this by hand, let's make it a very small sample set. Let's say 7, 4, 8, 10, and let's say 6. Okay. The sample, this is sample data. So we want to solve for S, find or calculate the sample variance, sample standard deviation and sample variance. So what do I do? First, I need to find the sample mean, X bar, which is the sum of all the X values divided by N. So 7 plus 4 plus 8, 10, 6, and then divide by 5. So what do we have here? 11 plus 18 plus 6, 35 divided by 5, 7. That's the sample mean. Okay, and then I'm going to make a table. X, and then X minus X bar squared. Okay, X minus X bar squared. I'm going to take each X value, subtract the mean, square the difference. So 7 minus 5 squared, that's equal to 4. Next data value, 4. 4 minus 5 squared is 1. 8 minus 5 squared, 3, square that, 9. The 10 minus 5 squared is 25. And the 6 minus 5 squared is 1. And then I'm going to say S is the square root of the sum. So what I'm going to do, I'm going to find the sum of these squares. 4 plus 1 is 10, 5, 10, 15, 15, 40. That's the sum of the squares. Okay, so I take the sum and I divide by n minus 1. Well, what is n in this case? How many values do I have? I have 5 minus 1. So square root of 40 over 4, the square root of 10, which is approximately square root of 10 is approximately 3.2. after rounding. Okay. So this is our hand calculations for finding the standard deviation, 3.2. Notice how I divided by n minus 1. Divided by 4. And then I took the square root. Okay. Your calculator will also give you the standard deviation. The sample standard deviation can be found with the calculator using exactly the same steps that I showed you for finding the sample mean. Okay. And then if I want to do the variance, the sample variance, which is S squared, what do? I don't go to my approximation. I go to the exact value, which is the square root of 10. And if I square that, the square root of 10, if I square it, the square is gone, square root is gone, so you get 10. Exactly 10 for the sample variance. Okay, any questions? All right. Something very, very important about the relation between the center of the sample and its standard deviation. Guys, focus with me on this rule. This is called the range rule of thumb for identifying significant data values. Very common, very useful rule that can be used to quickly identify and determine whether a given data value is significant or not significant. Okay. Suppose we have a sample. And here on the number line, I'm going to put in the middle here, the center here, X bar, the sample mean. And then I'm going to add 2 standard deviations, 2 standard deviations to the mean. So that will give me this mark here. And then on the left, I'm going to subtract 2 standard deviations. This mark here, X bar minus 2 standard deviation. Okay. So we have this range, which is the range of values within 2 standard deviation. Now, when I do a dot plot, if my data value is within this range, if my data value is here, or here, or here. All of these data values that you have in the dot plot, those are all considered not significant because they are within two standard deviations from the center. All of these are not significant values that are not significant. Now, if I see a data value, if I see a dot point that is more than 2 standard deviation to the right of the mean, then this is considered a significantly high value. Significantly high data value. Because it is more than 2 standard deviations away from the center of the sample. It's far to the right of the center of the sample. If I see a data value that is more than 2 standard deviations below the center, below the mean, like this one here, then this one is considered significantly low data value. They're considered significantly low because these values are more than 2 standard deviations below the mean. All of these values here, whatever values we see here, these are all considered significant. Now, if your sample data have normal distribution like this, then you will notice that you have very few values that are considered significantly high, because usually the bell curve has a tail, so right tail, so there are very few values that are significantly high. Right here, all of these values under the bell curve are considered significantly high, and under the bell curve, all of these values here in the left tail to the left of this mark, the 2 standard deviation mark, all of these values are considered significantly low. And the percentage of significantly high value is almost the same as the percentage of significantly low values because of the symmetry in the bell curve. Okay. And then the majority of the bulk okay. So we call the range rule of thumb for identifying significant data values. Any questions? Guys, are you with me? Can you please type yes? Okay, excellent. All right, Roxana's here. Okay. All right, so you see, guys, the relation between the center and the standard deviation. The center, the mean, gives you the center. The standard deviation gives you the spread. all the dots, all the points, data values within 2 standard deviation are usual values, are not significant. They are very close to the center. All the values that are more than 2 standard deviations away from the center, they are considered either significantly high or significantly low data values. Okay. And one more thing about from this section, we have what we call the empirical rule. The empirical rule for data with a bell-shaped distribution. The empirical rule. Let me explain what that means. I'm going to take a picture of this figure from the textbook. Give me a second. Okay. Suppose we have a sample data and we found that the sample data have normal distribution, a bell curve distribution. If we look carefully under the bell curve, if you look at the distribution of our data values, you will notice the following. Look, guys, at the number line. See, this is the center. This is 1 standard deviation above the center, and this is 1 standard deviation below the center. Within 1 standard deviation, which means this area here, you have about 68% of your data values. 34% above and 34% below, approximately. 68% of your sample data are within 1 standard deviation from the mean. 68%. If your distribution is a bell curve, if you have a bell curve distribution. Now, when you go 2 standard deviations above and 2 standard deviations below, x bar plus 2s and x bar minus 2s, then on the left, on the right, you have 34% plus 13.59%, which means a total 34. If you add those percentages, 34.13 plus 13.59, about 47% of your data values are above 47% above the sample mean and within 2 standard deviations. And then also on the other side, this value here plus this here, also 47%. The sum. This plus this here, 47.72%. If you add these 47.72 plus another 47, that will give you 95, approximately 95% of your data values are within 2 standard deviation. Okay, 95% within 2 standard deviation. So what is left, guys? We left with some data values here. These are the significantly high data values, approximately what, 2.14 plus 0.13, that's about 2 point, combined this is 2.27%, significantly high. And another on the left lower side here, under the left tail, also the same. If you combine these, 2.27%. These are the significantly low values. Which is, if you add the significantly low with the significantly high, 2.27 plus 2.27, approximately 4.5% of your data values are either significantly low or significantly high. But 95%, a little bit more than 95%, are not significant, are within 2 standard deviations from the center, within the center. Questions? Is everything fine, guys? Are you with me? Okay. All right. Section 3.3. Again, as I said, guys, the summer class is an intense class. We're covering material quickly so we can finish the course. So whenever you get the chance, if you can always review the notes and watch the Zoom lecture, that will help you remember the concepts that we discuss each time. Measures of relative standing. Okay, measures of relative standing. This section introduces measures of relative standing which are numbers showing the location of data values relative to the other values within the same sample. Okay. So I'm going to talk about something very important that can be used to describe the relative standing of data values. We call it the z-score or the standard score. Each data value has a z-score. So number one, z-scores. Now, if you have a sample, each data value in the sample has a standard score or a z-score. And the z-score for that data value is the data value minus the sample mean divided by the sample standard deviation. Okay? The z-score. So let's visualize this. Suppose I have this number line, and this is the center. This is the mean right here, x bar. And there is a data value, let's say to the right here. X is right here. I want to describe the position of this data value with respect to the center, to the mean. So I find the z-score. All right. Let's say, let's use some numbers here. Suppose that the center, the mean is 8. And let's say that data value that I'm showing you here is 10. And let's say the sample standard deviation is 1.5. Okay. So to find the z-score of this data value of the 10, what? I take the value 10, I subtract the mean, and then I divide by the standard deviation. So 2 over 1.5. And that gives me the z-score. 2 divided by 1.5. That would give me 1.33. Now, this is, again, another statistical rule. If you are finding the z-score of a data value, you always round the z-score to 2 decimal places. Round the z-score to 2 decimal places. 1.33. Now, this, if the z-score of a data value is 1.33, this means that the data value is 1.33 standard deviations above the mean. It is 1.3 standard deviations. Like when you measure distance, you will say, I am 5 feet away from this point, away from the center. Here in statistics, we're saying this data value, the 10, is 1.33. Instead of saying feet, it is 1.33 standard deviations above the mean. Okay. Now, what if my data value is below the mean? What if my data value is right here? Let's say X here is 4. My data value here is 4. What is the z-score of that data value? X is 4. Z-score of that data value is 4, the data value, minus the mean over what? Over the standard deviation, 1.5. Okay, so that means -4 over 1.5. See how the numerator is negative now? Because the mean is higher than the value, or the value is below the mean. So 4 divided by 1.5, and that would give me -2.67. Okay, see how the value is negative in this case? The z-score is negative here, and the z-score here is positive. So we have something very important, guys, here that we need to understand, which is the z-line. Here at the middle here, the z-score is 0. This is where the mean is. The sample mean is at it has a 0 z-score, and then all the data values that are to the right of the mean have positive z-scores. All the data values below the mean have negative z-scores. Okay. If a data value has a z-score that is greater than 2, if the data value is somewhere here, then all of these data values that you see here that have z-scores greater than 2, these are what significantly high values. Significantly high. All these z-scores that have, all these values that have z-scores greater than 2. All the z-scores that have, all the data values that have z-scores less than -2, all of these data values are significantly low. Okay, questions? Guys, you understand? Very, very important. Each data value has a standard score or z-score, and that score tells us how far that data value is above or below the mean. If the data value has a z-score that is positive, it's above the mean. If this data value has a z-score negative, that's below the mean. And the higher the z-score, right? Notice that statement here. The higher the z-score, the more extreme, the more significant the value is. The more significant or the more extreme the value is. Okay, let me explain with this example. And then we'll stop after this point. Okay, example. Which of the following two data values is more extreme relative to the data set from which it came. Okay. 99 degrees Fahrenheit temperature where the sample mean is 98.2 degrees with a standard deviation of 0.62 degrees. Okay, so this is my first value. It's a temperature value that belongs to a sample with this mean and this standard deviation, or this value, which is 4,000 grams weight, or 4 kilograms of a newborn where the sample mean is 3,152 grams with a sample standard deviation of 600 93.4 grams. All right, so I have completely different samples. One sample talks about weights of newborn babies, and the other one talks about temperature. And I have these two data values. Which one is more extreme relative to the data values that in the sample? Right? Is it the 99 degrees or the 4,000 kilogram? In order to compare these and see which one is more extreme than the other, we have to find the z-scores. Z-score of the 99 degrees Fahrenheit. What do? I take that 99 degrees, subtract the mean, and then divide by the standard deviation of that sample. Let's see here, 99 minus 98.2 divided by 0.62. 1.29. And then I do the z-score of the 4,000 gram weight. So 4,000 minus 31.52, and then I divide by the standard deviation, 693.4. 4,000 minus 31.52 divided by 693.4, and that gives me 1.22. Now let's compare and see which one has the higher z-score. Which data value has a higher z-score? It is the temperature value, 1.29. The weight, 1.22. So therefore, the result is the temperature is more extreme than the weight. Since the temperature has a higher z-score, then it is more extreme within its set. It's more extreme than the weight within the sample of weights. All right, so it's more extreme than the weight of 4,000 grams.